Well, good morning. This is Wednesday, the 12th of April, 2017, 8:16 in the morning. Sorry we're so late getting started, but my computer has been very slow booting, and PowerPoint very slow opening, and the Screencast-O-Matic very slow opening, and then too I had some issues. I'm not feeling very well this morning and was worried about even whether I was going to be able to make it, but I'm here, we're fine, but the trouble is I'm the only one in the class. This is Math 237, linear algebra. We're in chapter 3, determinants, section 3.3, properties of determinants, and about the middle of page 123. So since no one's here, I'd like to know if you had any questions, but since no one's here, we will get going on where we are. All right, I think last time we did finish the example 4, found the easy way to to determine the inverse of a matrix, the determinant of the inverse of a matrix. If it's an easy matrix to take a determinant of, take its determinant, and then the reciprocal of that is the determinant of the inverse. You don't even have to know what the inverse is, but it sure is a lot easier to, in general, to take a determinant and then take its inverse than to find the inverse and then take its determinant. So from there we move on to theorem, well, they refer back to theorem 3.7 and provides another equivalent condition that can be added to the list that we had back in theorem 215, and this list now summarizes 6 conditions of what it means to be a non-singular matrix, equivalent conditions for a non-singular matrix. Now what this means is this. Let me get my pen activated here. If A is an n by n matrix, number one, it's got to be square, right? Then the following statements are equivalent. Now what do we mean by this? If 1 is true, all 6 are true. Any one of the 6. And the order they give them here is not, a big deal. So what we're looking at is equivalent conditions for a non-singular matrix. Number 1, of course, if A is invertible, that means it's non-singular, okay? Those are synonymous terms, basically. Now, secondly, if AX equal B, okay, the matrix A multiplied by any old n by 1 variable vector X, and that's equal to some n by 1 variable, not variable, scalar value B, vector B, AX plus B has a unique solution. This we've hit several times before, okay, for every n by 1 column vector B. They call it column matrix. I just as soon call it a vector. Either way is fine. B. Every one, no matter what it is, even if that column vector B is a 0 vector, then there's a unique solution. Of course, if it's a 0 vector, that unique solution will be the 0, the trivial solution, which would be all the components of X would be 0. And that's what number 3 says, that the AX equals 0, and that's a 0 vector. They write it as if that's a number, but that has only the trivial solution. Okay? Number 4. And if any one of these are true, that implies all the rest of them are true, and also implies it's a non-singular matrix. Okay? Number 4, A is row equivalent to the identity matrix. And the identity matrix must be the n by n, or I sub n. That's one of the first ones we hit. I'm surprised that's not like 1 or 2 here. But again, the order doesn't matter at all. Okay? A can be written as a product of elementary matrices. That's what we did, what was it, last chapter? A can be written as a product of elementary matrices. Okay? That's what we did last time, and I think we got somebody coming in. Yes! I get so bored talking to myself. So I'm glad you're here. Okay. Flip out things here. I got a late start myself. My stomach's been upset today, or last night and today. So it was, nobody was here. I said, it'll take a moment. It turned out being more than a moment. This on the board. Let's do that.
Oh, that's right. I'm not going to be in the mix.
You're not?
Yes, sir.
Okay, you failed. Okay. All righty. We'll miss you. I hope somebody's here. Because by the end of the day, the way I'm starting the day, by the end of the day, I'm sure going to need some students here to motivate me. All right. And here now is the last. These are based on the last couple of theorems we did last time. What we're looking at are the conditions that identify what it is to be a non-singular matrix. Okay? Of course, it has to be square, or else we don't even consider it. So if A is an n by n matrix, all these 6 conditions, I haven't written the 6th one yet, if any one of them is true, then it's a non-singular matrix, and all of them are true. So pick one, identify one, indicate one, prove one. You know, if you find one's true, you know they're all true. That's what they mean by being equivalent conditions. And here's the last one. Of course, the determinant of A is not equal to 0. Okay? So, you need any time to digest that. It's in your book, page 123. So let's look, unless you got questions, at example 5. Now, before we go there, I didn't put it on Screencast-O-Matic because no students were. I was sort of late getting started. But since you're here, let me go on and say it so it'll be out here for all to hear. Today's a fairly normal day, whatever that means, you know. All right, both Williams brothers are here. Okay, good deal. But the rest of the week is not very normal, okay? All my classes meet a schedule. My office hours will be 3:15 to 5:15 as normal today. Now that's if my stomach allows it. I've been having a stomach problem last night and today, but I think it's getting better. But it should be, nothing should be different today. However, tomorrow, I will meet with my 8 o'clock class in the morning, and I'm going to try to come pretty close to finishing the 8 o'clock class, okay? I might end it a little early, maybe 9 o'clock. But the reason for that is we've got Honors and Awards Day over on the Birmingham campus that starts at 10, but they want students there by 9 that are participating, and they want faculty there. They may want us there at 9, but I'm not going at 9. I may leave here at 9 and get there by 9:30 or so. Because all we do is sit around or stand around, because most of the time where we are, there's no available chairs. We're in a hallway underneath the gym, and we just stand around leaning on the hall. It's just ridiculous to have us there that early. So I'm not going over to be there at 9. I will leave here around 9-ish, between 9 and 9:15. But then that wipes out most of my office hours tomorrow. Normally they're 10:45 to 1:15. Since the program is scheduled to go 10 to 12, and they just about always run over, the earliest I'll probably be able to leave to come back here is 12. That puts me back here at 12:30, so the longest my office hours will probably be 12:30 to 1:15, not 10:45 to 1:15, but the odds are it's even going to be later than that. Okay. Now, Friday then, normally I'm on the Birmingham campus 7:45 to 1. Not this Friday. I have an infusion this Friday. It's scheduled to begin at 8. That means I have to be there by 7:45. I will not be on either campus on Friday. These infusions, this new drug, I've been taking close to all day long, usually around 4:30 before I get through. So, and I'm not going back after it, okay, because I shouldn't really be driving much at all after the infusion. Not that the infusion's anything, but they give me 2 Tylenol and 1 Benadryl, and stuff that pretty much knocks me out. So I can drive home, but we live close. All right, we just had done the equivalent conditions for a non-singular matrix, which you see posted here. Let's move on to example 5, unless there are any questions. Are there? And just another reminder, since I won't see you until the day of the deadline, if you're interested in doing a Lawson Academic Scholarship application, get it in, or at least get it started this week, because the deadline is Monday. We'll see you Monday morning, and that will be, by end of business Monday is the last time to get those in. All right, let's move on to example 5. Which of the systems has a unique solution? Okay. Here is 2x2 minus x3 equal minus 1. 3x1 minus 2x2 plus 3 plus x3 is equal to 4. And 3x1 plus 2x2 minus x3 is equal to minus 4. Or 2x2 minus x3 equal minus 1. 3x1 minus 2x2 plus x3 equal 4. My writing isn't too good, but get over it. 3x1 plus 2x2 plus x3 is equal to minus 4. Now, which of those has a unique solution? Can you look at it and tell, or do we have to start row reduction? Okay, and let me point out to you, the only difference in these two systems of equation, this is a minus, that's a plus in that last line. Otherwise, they are identical. The first two equations are identical. The third one is very close to being identical, except for that x3, the sign changes. So my question to you, can you look at that and say which of those has a unique solution? You might even, it could be, I guess, that both of them did, but that's my question to you. Can you tell just looking at it? Or do we have to do row reduction? Which would not be a particularly happy thing to do, but it is doable. Can you look at that and tell? Second? The second one does have a solution. Why did you say that? I can't hear. Okay, very clever and good. If you look at the matrix, the coefficient matrix, it's exactly the coefficient matrix that we had for example 3. And that's what they did. Now, even if we hadn't done example 3, you can picture that matrix because the coefficients are there, and there's nothing that tells you that. Well, yes, there is. No, there isn't. Looking at the equations, but if you think determinants, because see, with equations, you have to do row reductions, you don't do column reductions. But with determinants, you can use rows or columns. So all you have to do is look at these two columns and say, hey, those two columns are multiples of each other. Multiply this one by a 2, and you got exactly that. And therefore the determinant of that is going to be 0, so therefore that will not have a unique solution. That's not the case there, and like you say, since it was just like the thing. Now, did this solution vector make any difference at all? No. It all depends on what's happening with the coefficient matrix. That's what determines it. In fact, since that does have a, what is the question, unique solution? Yeah. Since that does have a unique solution, you could put any vector b here. Make up any numbers in the world, and it still has a unique solution. Okay? Even all zeros, and then the unique solution would be the trivial solution, 0, 0, 0. Okay? Now, they went through and did the determinants. They had already done it, as you pointed out, in example 3. So why? I mean, seems like just sort of wasted effort. All right, so let's look at the last item in this section. The next theorem tells you that the determinant of a transpose, and both of you have books, so that's good, but I think still one person doesn't, so I'll go on and go in gory detail. That the transpose of a square matrix is equal to, let me start over. The next theorem tells you the determinant of a transpose of a square matrix is equal to the determinant of the original matrix. And that almost should seem, oh yeah, makes sense, okay? This theorem can be proven using mathematical induction, and theorem 3.1, which we did very first of this chapter, which states that the determinant can be evaluated using cofactor expansion in a row or a column. So guess what? If it's just a transpose, exactly what you did to the rows here, you're doing to the columns there. So guess what? The determinant's got to be the same. And here's what the theorem states then. If A is a square matrix, of course it has to be square for any of this to make any sense, then the determinant of A is identically equal to, no sign changes, nothing else, as the determinant of its transpose. Okay? So, they want us to show that, and that's going to be example 6. Hopefully it'll go pretty smoothly. But it's also, here's matrix A. All right, I think this may be a new matrix we haven't seen before, but no big deal. 3, 1, negative 2, 2, 0, 0, and negative 1, negative 4, negative 1, 5. Did I get it right? I think so. And what we want to do is show the determinant of that matrix is exactly the same as the determinant of its transpose. How would you do the determinant of that matrix? What would you use? We could expand it, repeat the first two columns and do our diagonals. I don't recommend it in this case. Why? The first thing I look at when I'm trying to determine the determinants is I look for zeros. Yes, look at that second row. Okay? the second column and third column each have 1 0. The second row has 2 zeros. Go for the maximum number of zeros. So what would you do then? You would do, if I could draw my lines, you would use that and go like that. Okay? Now, what's the first thing you have to determine here? How do you start that to get that determinant? Yes, it's a negative position. That 2 is in a negative position, so it becomes a negative 2. Why did that erase itself? I do not know, okay? But then take the determinant of what's left, okay? And what do you have left? Five minus I'm sorry, 2. So that would be negative 2 times 3, which is negative 6. Okay? Now we're to show that's the same as the determinant of the transpose. So let's first write what the transpose is, A transpose. You tell me what to write. In order to make it easier to see, I'll erase some of my construction lines here. Okay? Wait just a second. I have to get my pen back. Say again. 3. Whoa, it didn't take. Okay, say again. 3, 2, negative 4, 1, 0, negative 1, 5. Very good. He found the transpose pretty nicely. Now, how do you determine the determinant of that transpose? Go to the second column. You know, duh. I mean, it's the same. So use the second column, and that's in a negative position, negative 2 times, and this is exactly the same determinant that's left over, what you call the cofactor, okay? Exactly the same cofactor. So guess what? It's the same thing. It's got to be the same thing. That's what a transpose is. Okay, so therefore the determinants are that. Now they did in a lot more gory detail than I did, but there it is. Now, it's also bottom of the page, linear algebra applied, systems of linear differential equations often arise in engineering and control theory. The function f of t that is defined for all positive values of t, the Laplace transform, is given by this strange-looking integral, but it really makes for a useful device. So if we have time, we'll touch on Laplace transforms at the end of the term. I don't know if we're going to get there, but we'll try. Because we've now lost a week and a half of instruction. So we started the term on a Tuesday rather than a Monday, so we got 1 week or 1 day behind the Tuesday-Thursday classes then. Then we had Martin Luther King Day on a Monday, so that put us a week behind. And then we had rain day last week, wasn't it? And so that put us a week and a half behind. So I don't know if we'll catch up or not. But at least for now, you could write on who in the world is Laplace. Oh, let's see. Wait a minute. Let's see. This class, why am I going over this? Y'all everybody's turning the paper. Still may be something you might be interested in pursuing, is looking and seeing about that. And what's your major going to be? Mechanical engineering. From what they show here, those look like they could easily be a couple of mechanical engineers there, because it looks like you're working on a mechanical type issue. But I know in electrical things, and those may be power towers, I don't know. In electricity, they use Laplace transforms all the time. Mechanical, maybe not as much. All right. Homework exercises in 3.3. Do any of the odds 1 through 5. Any of the odds 7 through 11. Do either 13 or 15, or both if you choose. any of the odds 17 to 23, and any of the odds 25 through 29. Any of the odds 31 to 35, though they suggest 35 might be a little bit of a bear, in other words, saying use some sort of package on it. It's not so terribly awful because you do have at least one 0 in it, but it's still a pretty, it can take a little time, so consider that. Do any of the odds 37 to 43, and any of the odds 45 to 49. I would say do 51, and either 53 or 55 or both. I'll leave that up to you. And then any of the odds 57 to 63 that you choose to. Those are proofs or verifications or, things like that. So they're reasonable, but don't get too bogged down in them. Okay? True false, there's one there you could do, 65. You could do the other one, but the answer I think is given for 65. And then there's several sort of thought type things that you can do, 67, 69. But now, and this book does this, and it sort of irritates me, but they do it quite frequently. Here they introduce a brand new concept in the homework exercises. They don't mention it in the text, it's in the homework exercise. It's what they call orthogonal vectors. What in the world is an orthogonal vector? Okay, number one, it's got to be invertible, which means it's got to be square. So it's got to be an invertible square matrix. It's orthogonal if its inverse is the same as its transpose. Okay? If its inverse is the same as its transpose. So therefore, you know it has to be an invertible matrix, else it doesn't have an inverse. So, so it has to be square to be invertible, and it has, so that's what defines a orthogonal matrix. So if you want to take a look at any of the odds 71 through 75, there is a proof there, and then 79 is another problem with orthogonal matrices, an orthogonal matrix. Looks like a little bit of a bear, but see what you can do with it if you choose. You don't have to if you don't want to. And then 81 is another proof, and you can do that if you choose to. All right, any questions on 3.3? All right, let's move on to 3.4. The adjoint of a matrix, okay, these are applications of determinants. And we're not going to do this whole section, okay? There's a few things in here that get really bogged down easily, okay? But we are going to hit some of the beginning parts. First, the adjoint of a matrix. So far in this chapter, you have studied procedures for evaluating and the properties of determinants. In this section, you'll study an explicit formula for the inverse of a non-singular matrix and use that formula to derive a theorem known as Cramer's rule. Okay? You will then solve several applications of determinants. Okay? Now, back in section 3.1, the very beginning of this chapter, we talked about the cofactors. You remember that? Okay. Now, the cofactor Cij of a square matrix A is defined as that minus 1 raised to the I plus j power, okay, times the determinant of the matrix obtained by deleting the ith row in the jth column. So, if then you come up with a new matrix built with those cofactors, okay? Now remember, the cofactor includes the sign change, okay, and it involves the deal. Thank you. Excellent. And let me just say this, I appreciate you turning that in. I may not be quite as fast in getting it graded as I have been, not that I've been fast at all, but I had, and this is one reason I'm feeling kind of lousy today, we're doing budgeting for next year now, since I'm the department chair, and they have given me, I can't remember now, 5 different what do they call them? Budgets that I have to keep up with. 3 on this campus and 2 on the other campus. Natural science here, physical science there, math here, and for some reason English here, and math over there. And they separate the campus. So I had to do, and then this year they requested like 4 documents for every budget. Sorry about that. So anyway, I was here until between 9:15 and 9:30 last night getting those done, because the hearing is this morning at 9, which is starting pretty soon, and I'm teaching, so I couldn't be there. So I had to get everything to my boss yesterday so he would have them for the meeting this morning. So anyway, I'm behind in grading. These came in yesterday and I didn't have a chance. So as soon as I can get caught up in grading, I'll try to get those done.
No problem.
Hopefully over the weekend. Okay. All right. So what we wind up with, a matrix of the cofactors. Okay. Remember, the cofactor has the sign and the determinant of the minor. Remember the minor. So it's the sign with the minor. What you're missing here is the value of that one, that when you eliminate the row and the column, the value of that. They have the sign of it, but not the value of it. Okay? So, what that is then called, the transpose of your matrix of cofactors is then called the adjoint of the matrix. What? Why? Why would you want to do that? It sounds like a lot of mess. But let's do at least one so you're familiar with it. So let's find the adjoint of this matrix A. And this matrix A is -1, 3, 2, 0, -2, 1, and 1, 0, -2. I hope I copied it right. Okay. Now what we have to do is first find the adjoint of every stinking element in this matrix. Okay? So, let's start with 1, 1. All right. So, this is going to be the cofactor matrix. So let's call this the Cij. That's probably not the best thing to call it, but that's what I'll call it. Okay, this position is a positive position. Okay, forget about its value, -1 is a positive position, so you do the determinant of the minor that you have left. And what would that be? 4. Okay, done. Okay, what I'm going to do is go across that row and do each of those. So we'll wipe that one out now and forget about the 3, the value of 3, but we do remember the sign of that position. What's the sign of that position? Negative. So it's going to be a minus, and then do the determinant of that matrix, the minor. Second? It's going to be a -1, and you have a minus, so that's going to make the cofactor a +1. Okay? All right, we'll wipe out this, and now do that. Okay? What's the sign of that position? Positive. Forget about the 2, the value of it. What is the determinant of the minor? Not negative 2. 0 minus a minus 2, which would be 2. And it's plus because of the position. All right, this time, and what I'm going to do, and this is a little bizarre, just because I'm super lazy. Since I already had that one line through, let's go and do that one, which will be underneath the 2 there. What's the sign of this position? Minus, okay? And then what's the determinant of its determinant of its minor? Okay, it's a minus 3, and minus a minus 3 would make this a 3. Got it? Okay. Now I'll wipe out this one, and I can either do the first or second. Do you have a preference? Okay. Let's go on and do the first one. Okay. Now, forget the value. That's a 0. We wouldn't use it anyway, but we're not worrying about that. We're just looking for cofactors. What is the sign of that position? Negative. And what's the determinant of what's left? It's a negative 6, but you have a minus with that, so that becomes a 6. Okay? And then we'll do the middle value there. Never would leave that blank in tic-tac-toe, but we'll do that next. And what's the sign of that position? 0. No, I'm sorry. Yeah, positive sign. Okay, you got me saying it. And then what's the determinant? 2 minus 2 is 0. Okay. Now, strange again. I'm going to wipe out this and do the 3rd row. So we'll start in the middle this time. Okay, forget it's a 0. What's the sign of that position? A minus. And then what's the determinant of what's left? Negative 1, so minus a minus 1 is plus 1. Okay? And then let's go to the first entry on that row. And what's the sign of that position? Positive. And what's your determinant? Second? Okay, it's 3 minus a negative 4. Is what? 3 minus a negative 4, which is plus 4. 3 plus 4. 7. Okay. I thought you said negative 7. Okay. And then we'll do the last entry, the one we've been waiting for. This has been so much fun, though, hasn't it? Okay. That one. Okay. What's the sign of that position? Positive. And what's the value of the determinant of the minor? 2. Okay. Let me make sure I got the same that they did. 4, 1, 2, 6, 0, negative, 6, 0, 3, 7, 1, 2. So that's your matrix of your cofactors. Okay? But we really don't want to use that. What do we want to do? The transpose of it. So let's do the transpose of that, which I'm real tempted to call CJI, just because I don't need to write another okay, what would that be? 4, 6, 7, 1, 0, 1, 2, 3, 2. Okay. So, that is the adjoint of A. Okay? It's the cofactor matrix, the transpose of the cofactor matrix. Okay? So that's 4, 6, 7, 1, 0, 1, 2, 3, 2. All right. So what? The adjoint of a matrix A is useful for finding the inverse of A as indicated in the next theorem. Seems like I can probably write this right here since it has to do with it. So A has to be an n by n square matrix, of course, invertible square matrix, of course. Then, if that's true, then A inverse is equal to 1 over the determinant of A times the adjoint of A. Now that almost looks a little familiar, doesn't it? Okay? What does that remind you of? Your 2 by 2. Remember, we took the derivative of the 2 by 2 matrix, and then we didn't call it an adjoint then, but that's exactly what it was. Let's just take that 2 by 2 up here. Okay? Determinant of that would have been 2, so we would have done 1 over 2. And then you multiply that by the adjoint of A. Well, what was the adjoint of A? This is our new A, not this, but this, okay? What we would do, we would replace these two and negate those two. We would exchange these two and negate those two. Let's see what we got. Black out this row and this column, then that would give you a negative 2. That would be your determinant, right? Okay, and that would be your, what you would put right there, a negative 2. Okay, this one is a minus position, and it'd be a minus 0, so that would be a minus 0 there. And then here it would be a minus position, that would be a 3, so you'd have a minus 3 there. And then this would be a positive again, and that would be a minus 1. So basically what you did was do that. Okay, now, that gave you that thing, and then the transpose of that would then flip them right back to where they needed to be. Okay, so that's exactly what we did without calling it that, without going through a cofactor matrix or anything else. We could just do it because we just exchanged these two and negated those two, and it gave it to us. Okay, so. But this works for any size matrix. All right. They have a proof there, and you're welcome to look at it if you choose. Okay. And then their little remark there does the same thing I just did. Okay.
I'm not going to be able to come to Cal 3 today.
So this, Cal 3?
Yeah, because we got STEM white coat ceremony.
Oh, is that right?
It's
Okay.
at 2 o'clock.
At what?
At 2.
At 2 o'clock.
And I don't want to have to press for time from getting from over here to over
Right,
there.
exactly. Is Nigel in that too? Oh, he's not. Okay, because he said he wouldn't be at differential equations either, so y'all are dropping like flies. No, okay, just kidding. All right, we'll miss you. But I'll go on and finish the class online so you can follow. Get what you missed at the beginning, and now get what you're missing at the end. All right. So we're going to start this, since I've lost both of the students who were here. We're going to start with example 2. Okay? Now, before I erase anything, says use the adjoint of A to find A inverse when A is -1, 3, 2, 0, -2, 1, 1, 0, -2. Exactly what we had here. So we've already found the adjoint. Okay? So we're going to start from there and find A inverse just with what we've got so far. Well, the only thing we need is to determine the determinant of A. So let's get these construction lines out of the way here, and let's decide how we're going to go about deciding on the determinant. The determinant of A would then be what? We're using this, okay? Okay? Well, taking a look at that, you got 2 zeros there. You could expand and do your diagonalization, but that would be a little harder, I think. You got 2 zeros. They're not in the same row or column. So let's evaluate where they are. The possibilities would be the second row, the third row, or the first column or second column. Of those 3 choices, I like the first column best. Mainly because they're the smallest numbers, okay? Not that it makes much difference, but let's go with that and do our determinant based on that. Okay, so the first part we'll go across here, and we'll use a -1. Now we are doing the determinant now, not a cofactor, so don't get this confused. And then we'll do the determinant of what's left here. 4 minus 0, so that's -1 times 4. Okay? And then because of the 0, we can skip the next one and then do the third row. Okay? All right, I'm sorry. As I said before, I was here until between 9:15 and 9:30 last night, so that made me after 10 o'clock getting home, and by the time I ate a little something and took care of other things, it was already after 11, and so I didn't get to bed until after 11:15. I don't remember what time it was. So I'm sort of dragging today, and I started the week dragging, and I haven't caught up anything. So let's go on. This is a positive position here, so that's going to be a +1 times the determinant of this, and that's 3 plus 4 is 7. So that's +7. So -4 plus 7 is 3. Okay? What do we do with that determinant of A? We do 1 over the determinant of A, so that would be 1 over 3 times this adjoint matrix. 4, 6, 7, 1, 0, 1, 2, 3, 2. Okay? And what would that be? 4/3, 2, 7/3, 1/3, 0, 1/3, 2/3, 1, 2/3. There's your inverse of that matrix A. Okay? 4/3, 2, 7/3, 1/3, 0, 1/3, 2/3, 1, 2/3. Okay? Now, they say to check that and make sure that that is indeed the inverse of this. Now, one way you could do it is doing your adjoint. That's probably not the best word to use now. Append, or the identity matrix after A, and then do your row reduction. That wouldn't be terrible in this case, but it would still be very involved. Or the other thing is multiply those two together and see if you get the identity matrix. And that would be a little bit of a pain, but I think we can do it, so let's do it. Let me get my construction lines out of the way here. There, and there, and there. And let's see if we can multiply those two matrices together. This one times that one, okay? Certainly it's going to be a 3 by 3, okay? So let's take a look. I wish that I had 2 pointers, but of course this lousy old package doesn't have that. Neither did the other package table. But we have, let's do the 1, 1 position. I'm going to fill those in too. Blank, 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 blank. A 3 by 3 by 3 by 3 is going to be a 3 by 3. Okay? So let's do the 1, 1, which would be the first row times the first column. That would be minus 4/3 plus 1 plus 4/3. That's going to be 1. Pretty easy to determine. Now do your first row second column for that 1, 2 position. And that would be a negative 2, 0, plus 2. Sure enough, that's 0. So this isn't too bad, is it? All right, your 1, 3 position would be first row by your third column, and that would be minus 7/3 plus 1, or 3/3. That would be minus 4/3, and then a plus 4/3, of course, is a 0. So that's not too bad. Let's do the 2, 1. Second row of A, first row of A inverse, first column of A inverse. 0, minus 2/3 plus 2/3. Sure enough, that's a 0. Okay? 2, 2 position, second row of A, second column of A inverse. 0, 0, 1. Sure enough, it's a 1. Okay? Then, second row, third column, a 0, minus 2/3 plus 2/3, that's a 0. See, it's not too bad to do at all. And then, third row, 3, 1 position would be third row, first column. That would be 4/3, 0, minus 4/3. Sure enough, that's a 0. The 3, 2 position, third row, second column. 2, 0, minus 2, that's a 0. And 1 to go. And that would be the 3, 3, third row, third column. 7/3, 0, minus 4/3. 7/3 minus 4/3 is 3/3, which is exactly 1. All right. Now they suggest that we also do A inverse times A. I'll leave that to you if you really want to do it. It comes out just as easily. It's just reversing the order there and doing whatever. All right. So we have hit the adjoint. We see what it's good for. Another way of finding the inverse of a matrix. Now, is that easier or harder than doing the row reduction of the adjoint of the appended matrices? Frankly, I think it's not any easier because you have to go through and do every one of your cofactors, and then you have to do the transpose of that, and then you have to take the determinant of the original thing and then multiply it. I don't think it's any easier, okay? Perhaps, I don't even think you can program that to make it easier, okay? Maybe you can, maybe there's some decent little shortcuts there. I don't know. It's been a long time since I did any programming, but it just seemed like that would be a pretty big pain in the neck too. So, but it is another way you can get it, okay? Now we're going to look at another application. Section 3.4 is applications of determinants. And here is the one that I think, if you check with people who have done much of this, just about everybody knows Cramer's rule. Again, y'all have already all turned in, done your papers. Kramer's rule is named after Gabriel Kramer, and he used determinants. Kramer's rule uses determinants to solve systems of linear equations with n variables. This rule applies only to systems with unique solutions. Okay, so if you have one that you're going to have a parameters in and the infinite number of solutions, Kramer's rule won't work. Okay, so to see how Kramer's rule works, take another look at the solution of this, and this is probably easily going to eat up all the rest of the time we have. So I'll try to do it quickly. If we have a11x1 plus a12x2 equal b1, okay, a12 or 21, I'm sorry, x1 plus a22 x2 is equal to b2. There's your standard 2 by 2. Two equations, two unknown. Now, if you were doing this, typically the first thing that you would do is do a I'm going to try to get the order right here. We'll negate the top equation. In other words, let's see, solve for x1. We want to eliminate x2, so we're going to multiply the top equation. I hope I get this right. By a negative by a positive a22 and multiply the bottom equation by a negative a12. Yeah, I think that'll do it for us. Okay? And if you did that, what you wind up with is a11 a22 x1 plus a12 a22 x2 is equal to a22 b1. Multiply the bottom equation by minus a12 and you get a minus a12 a21 x1 minus a12 a22 x2 is equal to a minus a12 b2. Okay? Now, reason you did that, eliminate the x2, as I said before. Okay, add those two together, and you get a11 a22 minus a12 a21 x1 is equal to a22 b1 minus a12 b2. Okay, then divide both sides of the equation by a11 a12 minus a12 a21 a11 a12 minus a12 a21. Okay, I don't really need parentheses there, but I just put them. And you see what you've got here. This is what, because these go away, that's what your x1 is. And that's exactly what they've got here in the book. They put the B1 in front, B1A22 minus B2A12 over A11A1. Ooh. Oops. I divided here. I wrote a 1 rather than a 2. Yeah, so that's a 2. Okay. A11, A22 minus A21, A12. They write them in the reverse order I do, but it doesn't really matter. Okay. Now, out of time, but you can do the same thing for A to eliminate X1 by multiplying the top equation by A21 and the bottom equation by minus A11, and then you eliminate X1, you get X2, and you'll get a similar result, and that will give you X2 equal to, I'll write it the way they do, B2 A11 minus B1 A21 over same denominator, A11 A22 minus A12 A21. Okay, there's your X2. Now, we'll pick up and go from there next time. Okay? All right. Yeah, we did enough in here that you can start some homework exercises, I think. You can do any of the odds 1 through 7. You can try number 9. You can try 11 if you choose. You can try 13. It's doing something else. We're not going to do it in the text, so you could still try that. 15's a proof, so I'll leave that up to you whether you do. And stop there. We'll pick up with 17 next time. All right. Glad we made it through the class. Wow. Started with nobody, ended with nobody, but had 2 people here in between, which was good to have. All right, that does it for today, and we'll see you on Monday. Remember, I have limited office hours tomorrow, something around 12:30 to 1:15, and then no office hours on Friday because I've got an infusion that day. Okay.